Little quick review of area between two curves, and we're going to focus on also finding the area where there's more than two intersection points. So a quick review. Let's say we have a function y equals x squared and a constant function y equals 4. To find the area between those two curves, well, we've got a parabola, we've got a constant y equals 4, and we want to find the area that's bounded between them. So we have this area. I'm going to make it vertical. I'm going to choose to do this vertically. So I have a width of dx. So my integral has a width of dx, and the height of that rectangle is then going to be the difference between those two functions. So x squared minus 4 and dx. So the height times the width, and I want to sum all of those little rectangles, the infinite number of rectangles, from those two intersection points. By hand, we can just set the functions equal to each other. We obviously get plus or minus 2, and you get that solution. And obviously, we anti-differentiate that by hand or with our calculator and get the solution. Now, also keep in mind that in this case, we did upper minus lower relative to the x-axis. But there might be times when you don't know which one's the upper and which one's the lower. Now, again, if I switch these and had them backwards and did 4 minus x squared, I would obviously get an opposite answer of what this solution should be. But something to keep in mind is that we can always do this, because then it won't matter which one's on the top and on the bottom. This will always then give you the positive area between the two. So this will give you the exact same solution as this. Now, I don't know if we've introduced that yet, but that's a neat little shortcut if you don't know which one's on the top and which one's on the bottom. Well, that's going to come in handy when we do problems finding area between two curves with more than two intersection points. So I'm going to work with the function negative x squared plus 3x and a cubic of 2x cubed minus x squared minus 5x. And I encourage you to maybe do this along with me. Now I already have these in my calculator, so I'm going to turn this one on and turn this one on. And let's see what these look like. Here comes my quadratic. Here comes my cubic. There it is. And it looks like I have an intersection point down here and here and here. I'm actually looking for both of these areas. Now, if you look carefully, at some point within this interval on the left side of the y-axis, the cubic is above the quadratic. But then on the right side of the y-axis, the quadratic is above the cubic. So I would then need to, first of all, find those intersection points. And let's just do a quick. That looks like it's 0, 0. I'll make a quick little sketch here. Here's my quadratic. Here comes my cubic. So that is 0, 0. Oop, I guess I didn't do it completely. There it is, 0, 0. Second calc intersect. Coming over to here. G2. And my last one, intersect. That's it. -2, -10. All right. So now to set up my integral, or integrals, again, I'm finding these areas. I'm going to do it in terms of x, so my rectangles are going to be vertical. So I'll put a little dx there. So my first integral is going to go from -2 to 0, and I have my cubic function. Let's call this g of x, and let's call this f of x. So my cubic function minus my quadratic function. Upper minus the lower. And then I'm going to add the area from 0 to 2. Now the quadratic is on the top. That's my f of x minus g of x. And if I just now do a quick, so my cubic is, let's just check here. My quadratic is in y1, and my cubic is in y2. So if I now do a math 9, go from -2 to 0 of my g of x, so y2 minus y1 gives me an area of 8. Go and now change these from 0 to 2 and change this from y1 minus y2. That's also 8. Okay, so I get a total area of 16. But the nice thing, again, is that because we said earlier you can use the absolute value, it doesn't matter which one's on the top or the bottom, because it's always going to return it as a positive value. So I can instead, an alternate way is to go all the way from -2 to 2 of the absolute value of the difference of the two functions. And it really doesn't matter which one's on the top or which one's on the bottom. So I'm going all the way across the interval. So let's see what that looks like. So I'm going to go from -2 to 2, and I'm going to do value. And again, I'm just going to do y1 minus y2. And we should get what? 8 plus 8 should get my 16. And there it is. But just as a quick check, I'm going to go back and just flip it around just to prove. And it's also 16. It's kind of a slick way of not having to separate them, but to do it with one integral with the absolute value. Now, with that said, this works when I have my calculator. If I didn't have my calculator, I couldn't do this by hand. To actually do integration through an absolute value, you would have to actually write it as a piecewise function. And the pieces are going to be these two separate pieces. So this is a nice shortcut when you have your calculator. All right, let's maybe do one more. So I'm going to do y equals 4 minus x squared and y equals -x plus 2. Let's see what that looks like. They're already in my calculator. I would maybe suggest, if you want to, at this point, pause the video and find the area between those two functions. Okay. Now I'll continue here to see what this looks like. There's the quadratic. There is the linear. Should there have been more than 2 intersection points? Let me just check here quick. Oh, I forgot that this particular problem wanted to find the area between -2 and 3. I forgot that there was an extra added step here. So what's happening for this problem? So I've got my quadratic, and I've got my linear coming through. But if I look on my graph and hit trace, where is -2? -2 is back here. And where is 3? 3 is off of the screen. If I trace up onto the other line, 3 is right here. So there's -2 and there's 3. So I'm looking for this area, and this area. All 3 of those areas. While I'm here, let me get these intersection points. I think it's probably pretty obviously that that's 2, 0. Second calc, intersect. And this other point right here, I'm just looking in my calculator. I'm not going to assume anything. Again, I could be setting these equations equal to each other and solving my quadratic. So second calc, intersect. It's not far enough. Oops. second calc, intersect, I'm just gonna enter, so negative 1, 3. Okay, so again, by hand, if I was doing this by hand, I'd have to first find this interval. I'll call the quadratic f, and I'll call the linear g. So my first interval goes from -2 to -1. Now let me get in the habit here. I am doing this in terms of x. I'm drawing these vertically. Now, in other practice, we've done these in terms of y, but that means I would have to then rearrange and solve the equations for y. Why bother here? So -2 to -1, the linear minus the quadratic. So g of x minus f of x plus the integral from -1 to 2 of now it's the quadratic minus the linear. And lastly, from 2 to 3 of, look at this. This is interesting. Maybe I think I actually found the wrong area right here. I want the area bounded between the two functions. That's not right. So I actually want this area down in here. So that is now the linear minus the quadratic. And again, I could do all of these separately on my calculator, and you can try that and check that. But again, with one fell swoop, from -2 all the way to 3, those are x values, that's my width. I can do whatever function minus the other with an absolute value. So if I go on to here, so that's 9 from -2 to 3 of absolute value of, oops, I think these are in 3 and 4 for me. 3 minus y4 x. Thinking. So approximately 8.167. And again, I could switch them back and forth and we get the same value as well. So now give those a try. I think I've assigned a couple problems in Khan Academy to try. All right, good luck.